it's a funny thing. Engineers know this stuff, but the basic stuff I'm learning, they never really teach the engineers. So let's just say it's derivable from the from the knowledge they're given. The total knowledge can be derived, but they're never given the total knowledge, and so they're given a skewed version of reality. And then physics comes in and makes up the difference. So one of the things I notice that's imperfect is that when building a simple circuit involving a battery and two resistors of differing resistances, the tally sheet is you draw a diagonal line, and you have a ground. So you have a square shape. On one side of that square, you've got the battery. On another side, you've got the ground. And then two other sides, you have the two resistors, one each side. So you have to draw a diagonal line dividing the square into two halves, in which the ground side and the battery side are one side of that diagonal, and the two resistors are the other side. And then when you do a total resistance on the resistor side, and you do a voltage division computation to figure out the distribution, well, first of all, to figure out the amperage throughout the entire circuit. No, the amperage on this side of the line. The total the amperage on the resistor side of the line, so that you can then derive from that in combination with the two separate resistances, you can figure out the voltage on each resistor, and hence the watts. But now you have to go to the other side and transfer your information to figure out the rest of the other side. So the battery has two types of resistances. It has effective resistance, which is the result of the computation on the other side, and then it has the internal resistance of its construction. And of course, in simulators, they don't put one in there, so it's zero internal resistance. But a true battery has internal resistance. Usually, it depends if it's dead or not. If it's dead, it has more resistance. Let's just say it's 10 milliohms. It's actually, give or take, a milliohm or two, depending on whether it's dead or not dead. I believe it might be somewhere around 10 or 11 or 12 if it's dead. And it might be 8 or 9, maybe, I don't know, if it's not dead, something like that. I can't remember. For a nickel metal hydride battery, I'm referring to, from my dim memory. Anywho, let's just say it's 10 milliohms, regardless of whether it's dead or not, because in the simulator it's never dead. So let's just say it's 10 milliohms. You'd have to, that's a separate consideration than the resulting or the effective ohms. So if I have two resistors, if I have a 5-volt battery, one resistor is 3 ohms and the other is 2 ohms. The total resistance is 5 ohms. That means the effective resistance of the battery is -5 ohms. Because, see, a battery is a negative resistor whose voltage is always 5 volts for a 5-volt battery. But it's a negative resistor whose resistance is undefined until you hook it up to a bunch of resistive elements in a purely resistive circuit. Keep things simple for this discussion. But once you figure out what the total resistance is among your various resistances in the circuit, now you know what the effective negative resistance is of the battery. You know, this is all according to passive sign convention, but it makes sense because it is a negative resistor. Negative resistance has the capacity to generate current rather than consume it. So it makes sense that by implication, it's not enough to say that under passive sign convention the voltage is positive and the current is negative for a battery. You also, by implication, what you're also saying is that its effective operating resistance is going to be a negative resistance whose value is undetermined until you hook it up to a bunch of positive resistances. So in this situation it has -5 effective ohms. it has 0 internal ohms of its construction because it's a simulated battery. It's not a real live battery in the real world. And so we multiply the negative 5 ohms against the other two resistors created a condition of 1 ampere, positive. So when we get over to the battery side, see if I got this right. We don't know the amps yet, do we? But we know it's 5 volts. So we take the volts and of positive 5 volts, divide by the the total resistance, which is the effective plus the 0 internal, which is negative 5. So we take the 5 volts, divide by negative 5 ohms, and we get no, that's not right. Wait, no. Positive 5 volts divided by negative 5 ohms equals negative 1 amp, which is correct, because that's the way they like to do it. So I'm just trying to flesh out all the extra information they never bother to tell us that has to comply, due to Ohm's law. Everything has to make sense. So now the wattage would be the 5 positive volts times the 1 negative amp gives us a negative 5 watts. So it's a negative watt instrument. Meanwhile, the total wattage of the two resistors is positive 5 watts. The total resistance of the two resistors is positive 5 ohms. And I guess you could say the total voltage consumed by the two resistors is positive 5 volts. But the amperage is the only thing shared in common, and that's positive 1 amp between the two resistors, and of course negative 1 amp for the battery. Now, to me this is significant because this is what they expect us to comply with when we start to analyze circuits. Now the problem is, if you don't give the circuit the full amount of voltage, I know for a fact that the inductivity, or the current, shall we say, the current never saturates. It can never reach saturation. And if you have a condition of negative watts among your various components. So instead of having positive resistors, if we had negative resistors, magical negative resistors, which we can do, just not as a singular component, but we can construct an assemblage of inductors and capacitors and resistors and if we want to, we can add other things. We can add diodes and spark gaps, but that's extra. But with those 2 or 3 components, because the resistors are kind of extra too. Sometimes they're necessary, but sometimes they're not. It all depends on the situation, I think. But let's just include it for completeness, for the sake of completeness. So the use of resistors and capacitors and inductors arranged in a certain way can induce a situation in which they create negative watts among themselves. And that means, but in order to do that, our voltage source has to be significantly lower than the type of components that we're going to be working with. Otherwise, we got to increase the size of those components to humongous values that don't exist among man-made components, but they do exist in nature. When nature creates a thundercloud and creates all kinds of electrical activity, it's going to have huge capacitances, huge inductances, huge resistances, huge voltages, huge amperages, huge wattages, and so it can afford to get away with using large size components based on the fact that it's going to have inputted into the situation very high voltages. So you see, it's a question of balance, and if you want to create overunity in a teensy little man-made circuit, then you've got to supply it with a teensy amount of voltage in order for that voltage not to override what you're trying to attempt to do. Otherwise, it ain't going to happen. Because by definition, a voltage source is a source of voltage regulation. It's not just a source of voltage, it's a source of voltage regulation. They always leave out that little word regulation. and say, oh, it's a voltage source. No, it's a source of voltage regulation, just like a current source is a source of current regulation. So you're not just supplying current, you're supplying the regulation of current via the current that you are supplying, but coming from that current source. Likewise, you're doing the same thing, the similar analogous thing with a voltage source. Sorry for my coughing. I need to take more ginger. Too much dust in my house. So these are the kinds of things they leave out, and by convention, because nobody bothers to check. And it makes it easy for physicists to come in and say, oh, you got to have conservation of energy because your two sides of your circuit, or namely your equation, have to balance out to zero. Now this comes about due to a public policy that started in 1921 after a year of Treasury being bankrupt, and it's still bankrupt, and all banks are bankrupt. All of our because not our bank accounts, but our banks are bankrupt along with Treasury because of the reorganization they had to do once the Federal Reserve bankrupted this country. What they had to do was take up a new form of accounting, and that, or accountability among bankers and the Treasury for that matter, in that it's called double ledger, in which you add up all your assets, you add up all your liabilities in two separate columns. One's now you've got a subtotal that's positive, now you've got a subtotal that's negative, and they better cancel out and to get the grand total of zero, or else the banker has to make up the difference or lose their license. He has to make up the difference out of his pocket, one way or another, doesn't matter how he has to do it. It has to come out to zero at the end of business day every past midnight, whenever they do their calculations and money transfers or whatever, and they settle accounts. When they settle accounts in the middle of the night, sometime between midnight and dawn, they all settle their accounts, and it has to come out to zero for each one of them because there's no money in circulation. It doesn't exist. All we have are assets counterpoised by liabilities, and they have to cancel out. But in the world of free energy, it doesn't work that way. None of it works that way. There's no cancellation to zero. There's no logical cause and effect in time. You can have a diode consuming 10 watts and a coil of wire next to it producing 20,000 watts. It becomes a generator under the action of negative wattage, it's over unity. So that doesn't make any sense. No, excuse me, it's the other way around. No, I'm sorry. The coil is producing 10 watts, negative watts, and the diode is consuming 20 million positive watts. How can you do that and get away? And meanwhile, both of them, the absolute value, the absolute magnitude of both of them is still increasing. Now that can only happen because you've separated the voltage phase from the current phase by 180 degrees, and everything throws to the wind. All the logic and all the accountability of double ledger accounting goes out the window. Nothing adds up to zero anymore. It could be anything. Nothing is sequential in time. Cause and effect, a voltage source over here supplied you with 5 volts. 1 second later, what's going on? It's not logical. There's nothing logical about it anymore. Because the calculations for reactive power are so ridiculously insane. Once you get voltage and current separated by a half cycle of oscillation, it's so insane that logic is out the window. You can forget about it. So I better stop dwelling on this. So when we talk about saturability, current saturation, and its equivalency of magnetic saturation, we want a condition in which we put off saturation of current. Because if we do that, we can now get a rise of current, which we couldn't get before. See, before we had to get a drop of current due to resistance of various types. Some of them losses, some of them were appliances or loads, some of them were the internal loads of the circuit. And we end up with this flashlight circuit in which accountability, everything zeroes out to zero. But in this situation of over-unity, it doesn't work that way because we've extended the ability for the circuit to put off saturation of its current. And it's because of this negative wattage. Now, let's look at a battery. If we short out a battery with zero resistance, what are we going to see? We're going to see current rise to infinite value. Now let's say, we know this because if we use a very small resistor, let's say 1 pico ohm of resistance. No, let's do a little similar, easier. 1 milliohm of resistance. That means the amperages of coming out of that battery, going through that resistor, now our current is going to be 1,000 amps, right? So if we make the resistance ridiculously small, the amperage goes up. And if we make it 0, the amperage has to be infinity. Logic means that's your limit. So 0 resistance is your lower limit of resistance for the circuit to how effectively how quickly can you drain the battery. And the result will be infinity is your limit for how quickly you can raise the amperage up to quickly deplete the battery. Now, of course, if anything above what the battery was designed for will be an amperage too high for tolerance, and the battery will overheat and quite possibly explode. But just from overheating, it'll probably buckle and bubble, and because the stuff is boiling inside, all this heat is being generated because the battery does have internal resistance. See, the computer simulator doesn't have that, and so nothing happens to the battery. You can take it to infinite drainage, and nothing happens. It just sits there and gives you infinite current. But in the real world, that doesn't work that way, and so we get the battery melting, buckling, bubbling, and maybe even exploding in your face, and that's pretty nasty. All those chemicals. But that's the math. That's the way the math works. Now, that's because the battery was trying to approach its saturation of current. And it can only do that based on the resistances that are causing it to drain at a certain rate. It's a slave to the resistances of the circuit. It's totally dependent on what this total resistance the circuit is supplying to that battery. And if it's not supplying enough, it's going to rise. Well, whatever small amount it supplies, it's going to raise its current until it reaches saturation. So a battery can have saturation of current too. A voltage source also has current saturation, just like an inductor does. Only in the case of a battery, it'll be instantaneous. It won't take time to rise to get to the point of saturation. It'll just go there right away, and then you've got a mess in your face if you didn't plan accordingly in advance. That's why you got to plan. That's why engineers have to plan everything, because they don't want any surprises, ungodly surprises. So the battery is instantaneously going to its saturation point of current based on the resistances of the circuit. And based on those resistances, it'll go to its maximum current and reach saturation. Now, if you've got an over-unity circuit in which you're creating all of this reactive power, which is basically negative watts, so now it's not reactive anymore because we've combined capacitive reactance with inductive reactance simultaneously in both directions to the same degree of 90 degrees maximum in each case. So now we've got 180 degrees difference between them, so now we've got negative watts. A condition of negative watts, and so now it's not reactive power anymore. It's not usable because it's in the circuit where it doesn't belong. It was supposed to stay in the battery, negative watts, but now we've got it in the circuit, so it's not useful. In a sense, it's reactive power in that sense, that it's not useful unless it hits up with resistance, such as the resistance of the circuit, and it starts to boil and melt and blow up. So now it gets to go through what we tried to impose on the battery by not putting enough resistance in our circuit to drain the battery. Now in an over-unity circuit, if we don't have enough thickness, enough stoutness of wire gauge, and enough durability of the dielectric material used in the capacitors or the insulation on the coil, we're going to have meltdown and smoke and sparks and arcing. We're going to have a messy mess on our hands, and maybe something will explode, Maybe a neon bulb will explode, whatever it is, something nasty could happen if we don't size. So again, we have to plan. But in this case, the easiest over unity circuit that I find to make is one that rises over time to the point of infinite oblivion. Infinite oblivion meaning it's going to obliviate itself at some point, just short of infinity, but it's going to keep going to infinity until it obliterates itself. And unless you put regulation in of one kind or another, and that's the hardest thing in the world to do. So electrical engineers don't like to admit to this kind of thing because they consider it to be not only a safety hazard, but also to be useless. The fact is, though, it can be regulated, and you can get a constant output, which is greater than what you inputted. That is a fact of the matter, but it takes a great deal of dexterity. Now, how hard is it, though? Well, if you're at the top of the echelon of managing the utility grid, you'll know a few things that the technician in the field ain't going to know, or not bother to pay attention to, even if he did know. And so it'll be easy for physics to tell everybody what to believe in, making a religion out of electrical engineering, which was never there to begin with. They'll turn it into a religion. But the people who manage the electric utility at the top end of its design and management, they know. But the knowledge is apparently either given or dwelled on after it's been given on a need-to-know basis or a need-to-dwell-on basis. So if you don't need to dwell on it, you don't think about it. Or if you don't need to know it, you're not taught it. I don't know, since I'm not an electrical engineer, so I can't assume anything. But it's easy for them to deny this, in all honesty, this knowledge of free energy because they don't have to. Most of them, most of the time, don't have to admit to it because they don't have to deal with it. But if they do have to deal with it, they have to admit it to themselves at the very least. Because in managing the grid, you've got two factors. You've got how much reactive power is going through the system as well as the real power, and what is the nature of that reactive power. Is the capacitive reactance the same as, or I should say, the capacitive impedance the same as the inductive impedance? Because if it's not, you could get an explosion on your hands if there's enough overall reactive power to supply that difference of impedance to cause an explosion to occur. So they do know about this stuff, but they regulate the grid in such a way as to prevent it from happening, prevent an explosion from happening, prevent it from getting out of hand, which means they're not going to sit around and wait to see if they can create a condition of infinite rise. Now, Jim Murray and his friend did something similar. They didn't vie for infinite rise. They simply vied for targeted doubling the voltage and a substation. And they took the substation off the grid and isolated it so it wouldn't do damage to the rest of the grid if something should happen. And something did happen, something they couldn't have foreseen. They doubled the frequency. So it was 120 cycles per second. They doubled the frequency and the voltage quadrupled. And they didn't figure on that happening. It really, and they ran out of the substation before it blew up and caught on fire. It was really a nasty situation. And they walked away. Nobody knew that anybody who had done that, and they didn't tell anyone. And it wasn't a loss in the sense that it was a substation that was under use, so that if anything happened to it, they figured, nobody would care too much. Just the cost of either rebuilding it or just ignoring it would be written off. And that's probably what happened, one way or the other. But Jim Murray learned an important lesson, is that you can't always expect to know what the results will be. And this is why physicists are so wrong when they tell everybody what to believe in, because it only applies to a circuit in which resistive impedance dominates the situation or is exclusive in this situation, and there's no reactive impedance at all. Anywho, Wikipedia talks about this stuff, but this is beyond the measure that the consumer is accustomed to dealing with, and so they're given false information. The police do the same thing. If you ask them, oh, are the rules different about being naked at the beach versus being naked in the city street? And they say, no, the rules are not the same. But I know for a fact it is different. The law may be the same if you're not on city property that has been, has a city ordinance placed there for that jurisdiction, for that area of the city, city streets versus the beach. If it's city property, not all beaches are city property. City streets are. But there's no city ordinances on city streets for nudity, usually most of the time. And there's only ordinances against nudity on city beaches or city swimming pools, actually. So, in reality, the law is different. The reality is the law is the same. Let's say if state law would have the most, impact on the person. The law is the same whether or not you're on the beach or whether you're on the street. But the policy is totally different. And they'll never admit to it. Oh, no. Never admit to it. And you go into a swanky neighborhood, and it changes there too. Based on how much people will tolerate versus what they will not tolerate. Well, nobody knows any better about electrical engineering, so we tolerate this business of physicists telling us what to think and what to believe, which is only applicable under limited conditions of a flashlight-style circuit. And it doesn't apply to a lot of other circuits in which the reactive impedance dominates and the resistive impedance is negligible, at best. It's always going to be there, but it's so small that it doesn't count for much. Now, in some cases, resistance is a potential source of voltage. And we see that even in a flashlight circuit when we're doing the computations. We have to use the voltage of the battery, not its, not its current, to derive its current. Rather than just assuming, it's the same like it is everywhere else. If we had to calculate it, we don't know what the current is because but we do know what its voltage is. Right. Well, that's the case with the other. The other components. That's right. We derive the current. Okay, whatever. Voltage is a source of potentiality because if you put it in the right place of the circuit, it actually beefs up voltage, and in that area, and can beef up current in another area if it's a step down, step up voltage situation in which you've segregated. You have magnetic coupling between the two sections of the circuit. And you have high self-inductances on one side and low self-inductances on the other side, then you're sure as heck not going to want to have any resistance in the low inductive side, but you're sure as heck going to want to have it on the high self-inductance side to boost up your voltage even more so on the high voltage side, and then it'll step down when it bounces back and forth, sloshes back and forth between the two sides of the circuit. It'll deposit a gain of current on the low inductive side, and that's an advantage because then your overall power keeps going up. It's a self-feeding situation. It becomes self-feeding. But again, the saturation of current. So the main theme here is when current is separated from voltage by half a cycle of oscillation, you can never reach saturation of current so long as that condition is upheld. And because you've never reached saturation of current, anything goes. You literally have, the sky's the limit on how much energy you can create unless you program the circuit to regulate itself one way or another to prevent it from reaching infinite oblivion. And it's usually a pulsing situation. Solid state, it's very hard to get that to happen. Mechanically, obviously, you could have, or electrically, you could have transistors or relay switches That's always a problem, though. Will the mechanical relays operate fast enough? Will they get stuck in the on or off condition? That's no good. Will what's the other thing I'm thinking of? Oh yeah, will transistors burn up? And then you can't use them, and they're no good anymore, acting as a solid state switch. So there are all these contingencies you got to deal with, but one way or another you got to regulate it, or else it's just going to keep going to infinity, because it never reaches saturation of current. So this theme of current saturation is a very important theme, because if voltages should ever rise excessively, what happens? It arcs to the nearest grounding point, some point that has a significant voltage less than what's building up, and the air ionizes sufficiently to cause a pre-arcing channel of ionization which precedes the arc. And once that channel gets prepared and the voltage difference is high enough, it'll just arc over, and you've got yourself arcing going on. But that rise of voltage, there is no limit. There never is. We know that. It's the current that's the limiter. And it's the current saturation that's the limiter. In addition to that, there's also the current tolerance, which is another limiter, but that's a concrete world limitation. But the theoretical side is purely saturation of current, and that never reaches saturation if the current and the voltage are out of phase by half a cycle of oscillation. And now I'll shut up. But I think that's a very significant thing I'm finally learning.